Today, I'm going to talk about how we can develop our battery management system using Simulink, also introducing the main components of a BMS model that can be used for desktop simulation and testing purposes. We will go through how to start modeling our battery, how to develop control algorithms for state of charge estimation, and also the capabilities for hardware-in-the-loop testing. Welcome in today's webinar about battery management with Simulink and Model-Based Design, which is the first of our three-part webinar series of power electronics control design. My name is Ákos Pallag. I work as an application engineer at Gamax Laboratory Solutions. Let us start with an overview about battery management systems. First of all, what is a battery management system, or BMS? The battery management system consists of three main parts: the software, the electronics, and the battery pack itself. It is responsible for safe operation of our battery, its performance, and the battery life under different charge, discharge, and environmental conditions. So the main function of a BMS is to provide feedback and supervisory control that monitors cell voltage and temperature, estimates state of charge and state of health, limits power input and output for thermal and overcharge protection, also controls the charging profile, balances the state of charge of individual cells, and isolates the battery pack from the load when necessary. What are the main motivations in the development of BMS in Simulink? First of all, battery management systems has high complexity when it comes to designing the battery pack, the corresponding control algorithms for state of charge estimation and balancing. It could be challenging to include all elements from different domains to build up our BMS. Also, it is quite time-consuming to test battery packs for a wide range of conditions, code writing by hand, and using hardware prototypes for testing, which is also hard to reproduce or modify, and damages result in great costs. Furthermore, BMS are safety-critical systems, so the controls and the system must be in compliance with standards. Requirements must meet certifications like OSSAR and ISO 26262. All these challenges gave motivation to aid the development of battery management systems in Simulink. So with the modeling and simulation capabilities of Simulink, it enables us the BMS development, including the following: modeling battery packs using electrical network whose topology mirrors the actual system and scales with the number of cells. It helps us parameterizing equivalent circuit elements using test data for accurate representation of cell chemistry. It aids the designing of the power electronic circuit that connects the pack with the controls, helps with developing closed-loop simulation, closed-loop control algorithms for supervisory logic and also fault detection, designing state observers for state of charge and state of health estimation, and by using Simulink, engineers can exercise the battery management system over a range of operating and fault conditions before committing to hardware testing. You can generate C code from Simulink models to deploy your control algorithms for rapid prototyping of systems or microcontrollers. It generates code from the battery and electronic component models, letting you perform real-time simulation for hardware-in-the-loop testing to validate your BMS before hardware implementation. Later on, we will go through a BMS example model in Simulink to demonstrate the main modeling and control algorithm developing aspects. This is the BMS model in Simulink. The system itself has a model reference representing the BMS ECU with its various monitoring and control algorithms connected to a block with the representation of the battery pack and the associated circuitry and peripherals. By all these capabilities, engineers from different domains such as electrical, software, or thermal field can collaborate using Simulink as a common design platform. We create large system-level models to design and test BMS algorithm quickly, significantly reducing the iteration time of the design process. And our system can be met with several standards in the same Simulink platform to have a functional safety certification for our battery management system. In the next section, we will go through some ideas about how to create a Simulink model for a battery cell to be used in battery system design control. Developing a battery system using model-based design requires a model of the battery cell that accurately represents its real-life behavior and dependencies on environmental and operating conditions. For example, it needs to reproduce the voltage drop with time-dependent recovery following a current discharge event. Although it would be desirable to capture all the details of the electrochemical effects present in a battery cell, but control-oriented applications demand a more efficient approach that can be scaled up to battery pack levels and that is capable of real-time simulation. A widely accepted compromise between fidelity and simulation time is the equivalent circuit. The equivalent circuit is an electrochemical analogy with the aim of representing the behavior of an electrochemical cell using a relatively simple electrical circuit containing a voltage source and several resistors and capacitors that collectively reflect the open circuit potential, the internal resistance, and the relaxation time of the real cell. When modeling a battery cell using any given circuit, it is important to choose circuit topology and parameterization such that it can respond as similarly as possible as a physical battery cell. A typical equivalent circuit includes the voltage source associated with the open circuit potential, a series resistor related to the ionic conductivity of the separator and the electrolyte, and one or more RC pairs that represent the processes involved in the interpolation and the interpolation of lithium ions in and out of the electrodes. As far as the parameterization is concerned, it is crucial to capture the electrochemical and dissipated phenomena observed when testing a real battery, as well as their dependencies on states and environmental conditions. These requirements demand the use of matrices instead of scalar parameters that function as lookup tables and reflecting the physical behavior of the lithium-ion chemistry. One possible way to determine the characteristic parameters of an equivalent circuit is performing parameter estimation. Parameter estimation is an optimization-based procedure by which simulation result is compared against an experimental measurement, and the parameters of the model are determined in such way that simulation matches the experiment. It all begins by proposing an equivalent circuit architecture that we believe can represent the behavior of the real system. The initial parameterization of equivalent circuit is done using tentative values based on our experience. The simulation is set to reproduce the conditions of the discharge experiment. At this point, I'll take a simple battery cell example model in order to demonstrate the parameter estimation process. On the example model, we have the equivalent circuit for our battery cell represented by this table-based battery block and the current and voltage measurement by the sensor block. By clicking on this orange block, the parameter estimation app opens up. Let's take a look at the experimental data first. While current is flowing out of the battery, the measured voltage drops and then recovers after the pulse. The shape of the voltage drop in recovery is characteristic of these particular battery chemistries. The goal of this procedure is to be able to reproduce it using the equivalent circuit with the right parameters. More specifically, the series resistance needs to account for the instantaneous portion of the recovery. The combined RC pairs needs to explain the exponential portion of the recovery, and the voltage source must deliver the correct OCV as a function of state of charge. On the left-hand side, we can see the 4 parameters to be estimated. When we click on plot model response, we can see the mismatch between the response of our actual model with initial parameters and the experimental measurement. Simulink will work with optimization functions trying to minimize the difference between simulation and experimental data by adjusting the parameters of the equivalent circuit. This is done using a library called Simulink Design Optimization. When we start the estimation, Simulink runs the model over and over again, and every few runs evaluate how far it is from its objective, the experimental curve. While it is not close enough, it imposes perturbations to the values of the parameters to be estimated and evaluates if the change improves the situation or not. This is done in a very efficient way using advanced optimization algorithms. The present calculation takes a few minutes to converge. Simulink Design Optimization allows us the use of parallel computing in the options to distribute computational load in order to speed up the estimation process. Since it would take some time to run the estimation, I've already prepared the results. If I update the model parameters from the estimated results and plot the model response again, we see how the difference between simulation and the experimental data is minimized. If it's still not sufficient, we should change the topology of our battery model and do the parameter estimation again for that circuit. So we have seen how to find the best equivalent circuit and parameters that describe the behavior of a given lithium-ion battery cell. To perform this calculation, we made use of Simulink Design Optimization. To summarize, so we saw a method to create and parameterize an equivalent circuit for a lithium-ion cell using a combination of experimental measurement, simulation, and optimization. We started proposing an equivalent circuit topology and initial parameter of guesses. We saw how to create an optimization problem to calculate the parameter values with Simulink Design Optimization. The result is a battery cell block that contains the information to model the behavior of a real battery cell. And it is reusable in any system level model of an energy storage arrangement based on the type of device under interest. Now let's switch to our BMS model to see how the battery itself is described there. So this is our battery plant model. The variant subsystem on the left contains several versions of the battery pack. The small one with 6 cells and the largest one with 96 cells. Let's take a look at the small one. The battery pack is modeled in Simscape, where the component color tells us its physical domain. Blue indicates electrical and orange indicates thermal. We can see that the 6 cells are connected in series and can exchange heat with one another. The thermal layout is asymmetrical, with cell number 6 at the bottom insulated on one side, so no heat can dissipate in that direction. And cell number 1 at the top exposed to the outside atmosphere and therefore can get rid of the heat by convection. This asymmetry will be responsible for a significant temperature difference among the 6 cells. What makes this cell representative of a real-life lithium-ion chemistry? Well, inside each cell, there is an equivalent circuit represented by this battery block, whose topology and parameters should give me a response equivalent to the one I would observe experimentally. The equivalent circuit components should include temperature, SOC, and possible aging dependencies. The previously discussed method of parameter estimation naturally can and should be applied here. Next to the battery pack, there is a subsystem with the passive balancing circuitry, which will be described in more detail later on. A further element of the plant model is the set of charger and inverter contactor circuitry. Before connecting a battery pack to a charger, it is important to pre-connect them via a resistor to prevent an excessively high current from rushing into the pack and potentially damaging it. This pre-connection needs a special sequence that we will see when we describe the BMS algorithm. Finally, the last piece of the battery plant is the charger and the load, both simply represented here by current sources, commanded to follow the charging and driving profiles at the model top level. In the following section, we are going to discuss how we can achieve accurate state of charge estimation and cell balancing. Modern battery systems, especially the ones based on lithium-ion chemistry, require careful monitoring and control of state of individual cell to ensure safety of operation, good performance, and acceptable durability. One of the tasks of BMS is SOC estimation, which has crucial importance. State of charge is a relative measure of the amount of energy stored in a battery. It is defined as the ratio between the amount of charge extractable from the cell and the total capacity, all this at a specific point in time. Accurate state of charge estimation is important because battery management systems use the SOC estimation to inform the user of the expected usage until the next recharge, keeps the battery within safe operating window, implement control strategies, and all this ultimately improves battery life. Traditional approaches to state of charge estimation, such as open circuit voltage measurement and current integration, also known as Coulomb counting, can be reasonably accurate for cell chemistries with a significant open circuit voltage variation throughout the SOC range, as long as current measurement is accurate. However, estimating the state of charge for battery chemistries that show a flat OCV SOC discharge signature is quite challenging. Kalman filtering is a promising alternative approach that circumvents these challenges with slightly higher computational effort. Such observers typically include a nonlinear battery model, which uses the current and voltage measured from the cell as inputs, as well as a recursive algorithm that calculates the internal states of the system, including state of charge. Cell balancing is another important task of the BMS. Cycling a battery pack eventually causes individual cells to become out of balance, which yields typically from different Coulombic efficiency across the cells. It is undesirable because it limits the energy that enters or exits the battery pack, since the weakest cell limits the amount of charge that can be drawn from the entire system, and the strongest cell limits the amount to be discharged from the system. Balancing used to be done in two ways. Using a dissipative method referred as passive cell balancing, in which the excess charge from the cells is spread through resistors connected parallel with each individual cell. And by using a non-dissipative method or active cell balancing, in which the excess charge from some cells is redistributed among other cells that require it. Let's now focus on the BMS algorithm of our example model to present these approaches. This part of the battery management system monitors, protects, limits, and reports measurement from the battery pack. The subsystem on the top left uses individual cell voltages and temperatures to calculate maximum allowable charge and discharge current levels. While the cell is at low SOC, its voltage is low, and it's important to prevent the cell from delivering a large amount of current, since this would cause an excessively large voltage drop that could potentially go below the cutoff voltage. Comparing the minimum cell voltage in the module against its lower threshold and dividing it by the maximum internal resistance value calculated for this cell, we compute a voltage-based current threshold. We also know that it is important to limit current delivery when temperature is too high or too low. Using lookup tables with rising and falling profiles, we can specify a current threshold based on temperature and modulate the allowable current delivery. This is very important to avoid physical damage to the battery cell materials at high temperature, both during charge and discharge, and at low temperatures during the charging events, since doing it below freezing temperatures is not allowed. These two thresholds are then compared against each other, and the lowest becomes the current limit. The subsystem labeled as state machine defines the main operating states of the BMS. It is represented here using state flow, meant for designing state logic. In state flow, we use components representing states that are active or inactive, depending on the conditions. And the text we write inside the state is code that executes on entry during or no exit from the state. The state machine has 4 parallel states. The first one defines the variable BMS state, which indicates standby, driving, charging, and fault. The second state switches the fault state on in case of current, voltage, or temperature value reaches an unsafe level. And the third and fourth states define the pre-charger contactor on and off. So it provides the switching sequence for the charger and inverter. This is needed to avoid an excessively large current inrush at the beginning of the charging state. Let's see the state of charge estimation subsystem. Knowing how much longer we will be able to drive our car before we need to stop for a recharge depends on accurate estimation of the battery SOC. This is of great importance, and it is much more challenging than in the case of conventional vehicle, where the fuel level is measured directly. In battery systems, we do not measure state of charge. It's not directly measurable. We actually measure something else and hopefully relate what we measure with the SOC. The third subsystem contains 3 different methods for state of charge estimation. In practice, we would only choose one of them, but here we present all 3 to illustrate their individual limitations and behavior. The first method, known as Coulomb counting, consists of integrating the current that enters and leaves the cell to keep track of the state of charge over time. A benefit of this method is its simplicity and very low computational cost. Its drawbacks include the accumulation of current sensor error and its inability to recover from an incorrect initial condition because of the lack of feedback from voltage measurement. The second and third SOC estimation methods implemented here are the unscented and extended Kalman filters. Both are variations of nonlinear Kalman filters, and they rely on a model of unit cell to predict the terminal voltage resulting from a current stimulus, estimating the internal cell states by comparing this prediction against the measurement of the terminal voltage. The choice between UKF and EKF is typically made based on the severity of the system's nonlinearity. Kalman filter algorithm has two parts, the state update and the measurement update. The state update predicts the current state based on the previous state value and the input, and the measurement update corrects this prediction using newly acquired data. The next task to consider is balancing. It is important to keep individual battery cells roughly at the same state of charge. Otherwise, the cell with the highest SOC level will limit the amount of charge that we can put into the pack, and the system becomes underutilized. As I already mentioned in the battery plant model, next to the battery cell, the battery pack, there is a subsystem with the passive balancing circuitry. So the excess charge from the cells on top is led through resistors connected in parallel with each individual cells. Commanded by the balancing logic from the BMS algorithm, these switches selectively close when their corresponding cell needs a partial discharge to lower its SOC. The balancing state logic calculates the voltage difference between the highest and lowest cell voltages. And based on whether this difference exceeds a design value, it activates passive balancing. Balance command is a Boolean vector that indicates which resistor to activate so that the cell SOC is slowly reduced. Doing this with all cells except the one whose SOC is the lowest, eventually it makes all SOCs converge within a prescribed tolerance. Now, let's take a look at the simulation results. In this driving, charging, balancing sequence example, we first observe the individual cell voltages changing as a result of current flowing in and out. At the beginning of the simulation, they are slightly different because we initialized the model with a slight SOC imbalance. Towards the end of the simulation, the values converge towards one another as a result of the balance. Let's see the current. During the constant current stage, the current is derated during charge because the maximum module cell voltage is high enough compared to a prescribed limit that an excessively high current could drive the voltage beyond the threshold, and it would significantly limiting the life of the battery. The temperature traces show a significant difference among the hottest and coldest cell. The reason is mainly the asymmetry in the module layout in terms of thermal behavior. So cell number 6 gets significantly hotter than cell number 1 because it is thermally insulated on one side. Even when the maximum temperature reached during this simulation is not of immediate concern in terms of safety. The temperature difference, however, exhibited here, will eventually cause a much faster degradation of cell number 6 compared to cell number 1, leading to unevenness in cell condition, which is undesirable. Hence, the need for active thermal management to keep thermal differences within a few degrees of Celsius is necessary. The graph on the top right shows 3 SOC estimation traces of the same battery cell, each performed with the different methods. Yellow corresponds to Coulomb counting, blue corresponds to UKF, and orange to extended Kalman filter. The initial SOC in this simulation is 75%, but the SOC estimators were initialized to 80% in order to assess their capability to recover. It is apparent that Coulomb counting never does, because it has no way to realize it is wrong due to the absence of voltage information. But on the other hand, both Kalman filtering algorithms recover from the initial error within the first hour of simulated time, with the EKF slightly outperforming the UKF. Finally, the other two scopes indicate BMS states and each of the 6 balance command signals. In summary, we have utilized Simulink, Simscape, Stateflow, and control system toolboxes to design battery management system using modeling and simulation. In the last section, we will take a look into hardware-in-the-loop testing of battery management systems. Extensive end-to-end testing of battery management system, including all the possible fault conditions, is required to make sure that the system behaves as expected. Doing this type of testing for BMS can be very time-consuming. For example, before you start testing charging mode functionality, you must discharge the battery pack to appropriate state of charge level. Testing a complete charge and discharge cycle for a typical electric vehicle battery pack would take hours. And it's about days worth of testing when we include different operating conditions for temperature, for state of charge, and other parameters. Additionally, reproducing design issues and fault conditions can be difficult and involves safety considerations. While doing testing with actual cells, achieving test automation, test sequencing, and report generation can be very expensive and requires a lot of resources, especially when there is many test equipment involved. Doing extensive testing with an actual battery pack is required for final system integration test and functional test. But it doesn't make sense to do this type of testing for every software revision or design iteration. One way to achieve high confidence in your design iteration is by testing BMS controller and electronics against a simulated battery pack. This method of testing a real controller against a simulated plant model in real time is called hardware-in-the-loop testing. In hardware-in-the-loop testing, we start with plant model of a battery pack. This is the model you may have used for testing BMS algorithms in desktop simulation. Next, we generate C code from the battery model and compile into a real-time application, which gets deployed and executed in real time by a dedicated real-time target computer. This target computer must have required peripherals to convert numerical values into physical signals, such as cell voltages or temperature. We connect peripherals of the real-time computer with BMS controller to perform closed-loop testing. By replacing the actual battery pack with a programmable one, we can now perform end-to-end testing of software and electronics more efficiently and safely. It results in reduced testing time, the safe testing of fault conditions, and the capability of automate testing. Now, there are a few things we need to take care of before we can do hardware-in-the-loop testing for the BMS controller. First, we need to run the model of large networks of cells in real time at the step time required by the BMS controller. For the most common battery application, BMS algorithms get executed between 100 up to 500 Hz. So executing our battery plant model at 1 kHz in real time is more than sufficient for field testing. The second challenge is related to the hardware. Since we want to emulate the electrical behavior of a battery cell, we need to have ways to produce isolated voltages and be able to connect them in a series or parallel configuration, just like actual cells. Additionally, we will need temperature sensor emulation and fault emulation as well. The first step of going from desktop simulation to real-time testing is by selecting a right fixed step solver for our Simscape network. We must use a fixed step solver that provides robust performance and delivers accurate results at a step size large enough to permit real-time simulation. For real-time simulation, overruns must be avoided, so when the execution time is longer than the sample time, must be prevented. To do this, we run a fixed cost simulation, limiting the number of iterations per time step. The iterations in Simscape are limited by setting the checkbox and entering the number of nonlinear iterations in the solver configuration block. For the best balance between accuracy and cost, we would recommend to initially setting the number of nonlinear iterations to 2 or 3. We also note that for certain topology, partitioning solver improves the performance by reducing computational cost of simulation. This helps in achieving faster simulation rates for both desktop simulation and real-time testing. The partitioning solver converts the entire system of equations for the Simscape network into several smaller sets of switched linear equations that are connected through nonlinear functions. Computational costs are reduced because it is more efficient to calculate solutions for several smaller equation systems than it is to calculate the solution for one large system of equations. As we add more complexity and details in the model, it is very possible that we may not be able to achieve desired sample time just by selecting the right solver. In this situation, specific to battery modeling, we have a few more options that we can consider. The first option is to select a right variant of the battery block. Here we can notice that by selecting a right variant with lower fidelity, we can easily gain 10 times reduction in task execution time. Another option is to select lower order dynamics of battery cell. This also helps in reducing task execution time significantly, which gain in performance is coming from reduced fidelity also. As we discussed earlier, the second important aspect of doing hardware-in-the-loop testing for BMS application is to emulate sensor signals and sensor faults. For emulating cell voltages, Speadgoat provides a battery emulator card. Each battery emulator card provides 6 isolated channels. Each channel can supply up to 7 volts, which allows us to simulate different cell chemistries. Additionally, each channel can source up to 300 milliamperes and sink up to 100 milliamperes. Also, multiple I/O modules can be combined in series or parallel to achieve the required power levels. In addition to battery voltage emulation, we need temperature sensor simulation cards and fault insertion cards to complete BMS hardware-in-the-loop setup. Speadgoat provides various options for temperature sensor emulator card and fault insertion. In summary, we saw how we can use Simulink as a common design platform for different domains that can be used by engineers in our team from different fields of engineering, which also helps us to reduce the iteration time of the design. We can create large system-level models of BMS algorithm for designing and testing purposes that still use the Simulink platform. And the built-in tools aids us to have a functional safety certification for our battery management system before implementing it to real-world application. I want to thank you for your attention, and I would like to encourage you to reach out to us in the future via email if you have any questions or you need support in the BMS matter or in any other topics. Thank you.